पुरानी वाली उड़ा दूँ ना?
किसका?
फिजिक्स सॉफ्ट ग्रुप में लिंक है ना, फिजिक्स सोसाइटी ग्रुप में ये उड़ा दूँ
क्या?
दो मैसेज।
अरे वो लिंक चेंज हुई है।
लिंक चेंज सेक्सी हो गया। ऑडियो
भाई भेज दो।
हाँ ठीक है, कुछ नहीं। ऑडियो
भाई
मेरे फोन नंबर याद है।
हाँ
It's cross.
माइक का कैसी नहीं माइक
मैं निकलूँगी पहले। बिल्कुल।
Good evening, everyone. A very warm welcome to each one of you for this 2 days lecture series brought to you by Physics Society's Astronomy Club and Payment Club. We have gathered here to embark on an enlightening journey through the realms of physics and astronomy, exploring the mysteries of black holes in our universe. This lecture series represents a convergence of minds passionate about unraveling the secrets of the universe, and is honored to have you all with us. I'm honored to introduce our esteemed speaker, Professor Dhruva J. Saikya. He is the head of Teaching and Learning Center and National Resource Center for Astronomy at IUCAA Pune. Please join me in extending a warm welcome to Professor Dhruva J. Saikya, and we look forward to the enlightening lecture ahead. Welcome, sir. So, without further ado, let's dive into this intellectual odyssey with curiosity as our guide and stars as our inspiration. Over to you, sir.
Thank you very much. Okay, thank you very much for this kind invitation to actually speak to you all this morning and on the theme of black holes. And I will deal with black holes both from an observational perspective to show you the kinds of objects, the kinds of massive objects that exist in the universe. Now, what I would like to say right at the outset is that feel free to interrupt if you have a question. And if you don't ask me questions, I may ask you questions in between. So try and make it as interactive as possible. Am I audible at the back? You it really clearly?
Go inside.
So all of you recognize this picture which was splashed across the newspapers a couple of years ago? Yeah? Yes. So this is the image of a black hole in a nearby galaxy called Messier 87. And if you're wondering how it got its name Messier, Messier was an astronomer who was interested in comets, but he catalogued a whole lot of diffuse objects so as not to confuse them with the comets he was trying to identify and look for. So they consist of all kinds of objects. They consist of nearby galaxies, they consist of star clusters, they consist of diffuse nebulae, which could be balls of gas which are ionized by hot stars, or the remnants of massive stars which have exploded. But this particular object is an elliptical galaxy. An elliptical galaxy is one which just looks elliptical in the sky when projected onto the plane of the sky. It could be like an egg, which is called a proline, or it could be like a bun, which is called an oblate. When projected onto the sky, it looks like an ellipse. But on the other hand, there may be no special axis of symmetry either, okay, which are called triaxial ellipsoids. So astronomers spend quite a bit of time trying to understand the intrinsic shapes of galaxies to try and get some clues as to their physics and how they may form, how they may evolve, etc. The reason why I'm showing you this galaxy is that this was the first black hole to be actually imaged. And to image a black hole, you need very high angular resolution. As we shall see in a short while, that this image was made with telescopes which were located from right in the South Pole to the Hawaii Islands to Northern Europe. Because the angular resolution, as you have studied in your undergraduate classes, is given by lambda wavelength divided by the size of the aperture, right? What is the resolution of the human eye? Roughly. Sorry? You just try to calculate it and convince yourself it's roughly of the order of the nanometers. With 550 nanometers for the wavelength of light, few millimeters for the people, it will vary during the night and day, but of that order. You know what is the resolution to image this particular black hole? What you see over it, the black part is where is sort of the photosphere, just outside is the photosphere. So right from the black hole, we cannot get light, right? Light even does not escape. But the resolution angular resolution to be able to image this black hole in a relatively nearby galaxy is about 20 micro arc seconds or so. We said about an arc minute, this is 20 micro arc seconds, or 10 to the power 6 times so. To get a perception of what that means, then if you took an apple and put it in the moon, you'll be able to say the structure of it. So that's the kind of resolutions which astronomers have been able to achieve by combining data from telescopes. So you can't build a single aperture that big, but techniques have been developed where you locate antennas in different locations, but you combine the signals in such a way that it mimics that upper margin. Okay? It's a similar telescope, not as high resolution, which our group had built called the Giant Video Wave Radio Telescope, which is located about 80 kilometers north of Pune, where the separation goes to about 25 kilometers. Very small compared to the Event Horizon Telescope, which extends for thousands and thousands of kilometers. But still, the techniques are similar. Now, the story of black holes is intimately related to the story of jets in active galaxies. All right? What does the story of jets mean? What do you understand by a jet? The immediate perception when you think of a jet is something which is moving fast, isn't it? Jet planes and jet trains and okay. So these are actually collinear ejections from a black hole of relativistic plasma at velocities very close to that of light. Not all black holes actually emit such relativistic jets, which actually go out or squirt out from the nucleus of an active galaxy like M87 at nearly the velocity of light. How these jets form, how do they get accelerated to such speeds, what makes the black holes do that, why don't all black holes do that, are still questions which are at the frontiers of research. Let me just, for a historical outline, let me tell you a little bit about this particular jet in M87. There was a jet which was detected. It was not called a jet jet, but a narrow filament way back in 1980, early part of the 20th century, by Curtis, who talked about a curious strange space ray rising at the top of the universe. This is a more modern image. This is a more modern image. More modern image taken at infrared wavelengths, and this is a feature which we talk about. At that point in time, one did not know about jets. One did not know about black holes, but one just knew before was able to detect a thin line of water, and that is where the story ended for quite some time. This particular galaxy is also by HGC 486. You see these names when you look at astronomical literature. It was quite a few years later, in 1954, that was the first time that the word jet was used. In fact, British astronomy had started off in the 1930s when the jet was the source of image, and what we found was that they could measure a shift in the spectral line from the base of the jet. What does a shift in the spectral line mean? If they assume at least that the material is moving. Okay? And how do you know it is actually moving towards you? Is because the velocity is negative relative to the systemic velocity of the galaxy. What do I mean by systemic velocity of the galaxy? That one of the profound discoveries which was made in the early part of the 20th century by Edwin Hubble with contributions from others is that the universe is expanding. And all galaxies are moving away from each other. If the galaxies are generally moving away from each other, then what you will get is that the spectral lines will shift towards the red end of the spectrum. So if from a particular galaxy you get something which is blue shifted or shifted to a shorter wavelengths compared to the systemic velocity, then it means that the material is coming towards you. Alright? Now, that was the first time our jet was used, and you can see that the jet is actually one-sided. Right? It's a question which there is, if there is time, we will try to address, but there is a jet on the opposite side. How do I know there is a jet on the opposite side? In this particular image, which is an infrared image, I should say a little bit about observations at infrared and radio wavelengths, is that when light comes towards us, it gets scattered by the gas, it can get absorbed or scattered by the gas and dust which exist in these galaxies. But the longer the wavelength, the less is the effect. And that is why the sun appears red, sunrise and sunset, the longer wavelength red light comes through, whereas the blue light gets scattered more. Similarly, and from the deep interior regions of galaxies, you can see it far clearer if you look at longer wavelengths. And what you see in the longer wavelengths is that there is a bow shock kind of material, which is a shock wave which is created on the opposite side as well. There's a little bit on this side which does come out very well, of a jet which is on the opposite side. So we know that these jets which come out, squirt out from the black holes are actually two-sided. Although very often we only see one side. Okay? Just keep that in your mind somewhere, and we will try to address it depending upon how much time we have here. Okay? Now, I will show you a radio image of this object. This is an object of M87 at various scales. This is a block of, oops, sorry. So I show it, huh? So let's keep this up. Alright. So what you see over here is a video image of this. You can see a one-sided jet working out, and what happens is the jet all consists of relativistic electrons traversing at the velocity of light, and the emission which you see at radio frequencies is because of what is called, we just studied about cyclotron radiation in your undergraduate classes, but there the electrons are non-relativistic or at most mildly relativistic. But when you accelerate these electrons to velocities which are nearly the speed of light, 0.999999 goes on, then it is what you call synchrotron radiation. Okay? So these are highly energetic particles moving in the magnetic field decaying typically of a few microgauss or so in these extended lobes of emission, where you see the extended structures. Now the extended structures which you see can actually go up to several million light years across. So you have jets of plasma created by supermassive black holes which can squirt at a velocity of light and traverse billions of light years across. In fact, some of the largest ones are where if you had 100 Milky Ways lined up, one next to the other, you'd be able to cover from end to end. That's the kind of sizes. So there's a lot of interesting physics in trying to generate this kind of energy, collimate it, and also they can traverse over such large distances without the development of instabilities that may disrupt economics. So you have structures right from a small fraction of a light year. You can see over here the Event Horizon Telescope to actually hundreds and hundreds of kilometers. This one is a relatively small object compared to some of the largest objects that we will encounter today. Here again you see that the radio jet is one side, right? Just to give you another example of a radio source, these are relatively nearby galaxies which have been imaged with very high angular resolution. Effectively, this has been done with the Event Horizon Telescope, as it is called, because with the kind of angular resolutions you can get for the nearby objects, you obviously get more physical resolution, right? The linear size, and also the object is brighter because it is relatively nearby, making it easier to observe. And you can see the physics of how these jets actually are squirting out in this sheet of emission. It is not being filled up. So these are the kinds of results which have only come out within the last decade or so. So physicists or astrophysicists who work with jets, trying to see how they are correlated, we try to image the magnetic fields around it, look at the structures, see where the jets actually originates. So today, at millimeter wavelengths, we are able to approach at least hundreds of times the Schwarzschild radius. We'll come to what's a Schwarzschild radius in a short while, for those who are not familiar, but we'll just move on with the story right now. So this is just an image of the Event Horizon Telescope, which I referred to earlier. The telescope at the South Pole over here, to Greenland, Northern Europe, Hawaii. So building up very long baselines for observations to map the nuclear regions of these galaxies. Okay. Now, just to give you an idea of the resolution, I mentioned about the atom on the moon. You take a 5 rupee coin, and put it at a distance of 100 meters, it will subtend an angle of about 47 arc seconds, which is roughly about an arc minute, which is about the angular resolution of the human eye. What is routinely observed today by combining signals from antennas across the Earth is at a milliarc second level, which is a 5 rupees coin at a distance of about 1,000 kilometers. So there are regular arrays of telescopes in Europe and in the United States, and globally as well in China. And recently the GMRT also took part with the telescope, which is located here fully, in combining the signals with global telescopes to achieve high angular resolution to look at the nuclear regions of active galaxies and other compact objects as well. So now I mentioned about the jets being one-sided. I talked about radio galaxies, and I talked about the elliptical galaxy that is associated with the jet which is in the sky. An exotic class of objects which you would have met perhaps in the popular literature are the quasars. Right? The short form is for quasi-stellar radio source. When radio astronomy first started out, they made images of the sky at radio frequencies or radio wavelengths, and they found blobs of emission in the sky, but you couldn't really say where they were or what they were associated with till you tried to find optical counterparts. So some of the objects which I showed you a short while ago, the elliptical galaxy M87 and the nearby galaxy Centaurus A, which is visible from the southern hemisphere, are relatively nearby objects. In the early days of astronomy, the angular resolutions of the telescopes were small. So if the galaxy is nearby, the angular size of the telescope of the galaxy is also large. So if they coincided, you can hold your heart in your hand and say, I think they're related. But what happens is that when the objects are more distant, within your resolution element, there may be 100 optical objects. So you don't really know which one is likely to be associated or none at all perhaps. So in that exercise, there was this very powerful radio source, cataloged by the third Cambridge survey, which took place in the late 50s and early 60s. and it was associated with a star-like object. And stars are not known to be strong radio sources. So it was a puzzle as to what is the kind of object which we are seeing. Okay? But you needed an accurate position. You didn't have the resolution. But Cyril Hazard in Australia, he came across this clever thing to do. He says, well, the source appears to be going behind the moon, and I know accurately the position of the moon, and when it cuts across to the lower position of the moon, I can determine the source. We've learned about diffraction, and what happens is that the straight edge of the moon acts as a diffraction pattern. If your source is a point source, you get a sharp diffraction pattern. If it's blurred, your fringes are going to go down. So similarly, you can look at the fringes, basic applications of physics which you do at the undergraduate level, but on a cosmic scale, and infer whether the size is compact or it's big. So to measure an accurate size, we could identify it with a star-like object, but lo and behold, the story didn't end there, because stars, if you read a little bit about it, are characterized by absorption lines, absorption of light with the cooler outer layers of the photosphere to continuum light comes from side to side. This one had very prominent emission lines. And they couldn't actually identify the lines in the beginning. Then Martin Schmidt, a very well-known astronomer, realized that if you took the Balmer spectrum and just shifted it, it would fit exactly. That means it was an object which is outside our galaxy. It was an object which is participating in the cosmic expansion of the universe. And by how fast it is moving away, you can estimate the distance. So you had a star-like object. Okay, which when you calculate the distance from the redshift, was amongst the most luminous objects known at the time. There are thousands of stars brighter than this, if you just look at stars. But this was heralded the discovery of quasars, and when you look at the luminosity, you can see that it is about 10 to the power of, this is the range of this kind of object, 10 to the power of 46 or something. And the reason I'm showing you this is related to black holes as well, because this is the jet of collimated plasma which was mapped right from the early days. And this particular jet is seen at radio wavelengths, it is an image of optical wavelengths by the Hubble Space Telescope, and in X-ray wavelengths at the highest energies it is seen. Today we will perhaps not have the time to understand the physical processes that are going on, but again you can see that the jet is highly asymmetric. You can ask yourself the question, is this object different from a galaxy? That is a question which is posed right from the beginning, and the only way to see it is to see if this very powerful star-like object has a galaxy around it. Now just like when the sun is out, you don't see the stars. So if the nucleus of a galaxy is extremely bright, you may not see the galaxy around it. Also, when you observe from the ground in those early days, the atmosphere will scatter the light and make the image about a lot broader. So for these distant objects, the galaxy angular size would be also small. So if you made the image of the object large, you would not be able to see the galaxy. But the Hubble Space Telescope made a major advance. It detected the surrounding galaxies around almost all the quasars where it could, with confidence, be able to detect it. And we now know that quasars are nothing but galaxies with abnormally luminous nuclei. Okay? So quasars are the galaxies, and they are also powered with jet emission, which you see, which are again collimated emission of relativistic plasma, very well collimated at velocities nearly the velocity of light. You can actually measure these velocities by looking at motions of knots by these very high resolution observations and infer the velocities. And due to geometric effects, it actually appears to go even faster than the velocity of light, although that is not a physical velocity with which it goes. Now, huge amount of energy which we see from these objects can be understood in terms of accretion onto a supermassive object. Let me just mention, without getting into too much of details over here, what happens is that if I drop this, I will not throw it and break it, but it will build up kinetic energy, right? So when it hits the ground, that kinetic energy will have to be dissipated somewhere, right? It will break the pointer, but it can also go into internal heat of a system. Okay. Now, when we look at the physics of transfer of energy out of the conversion of potential energy into other forms of energy, we find that this is far more efficient to do it than even the nuclear reactions which occur in the centers of science. Particularly so if the black hole is actually spinning. Because the black hole, as you can visualize, that it is a point-like object. So if you just drop it and it falls radially, it's just going to go through and we lose it forever. But what happens is that matter which falls into a black hole usually has a certain angular momentum associated with it. And the angular momentum leads to the formation of a disk and dissipation of energy into the disk, and some of it is, we believe is to be collimated into these jets with the help of magnetic flux and also extraction of radiation energy. Now the last stable orbit around the black hole is actually closer to the black hole when the black hole is rotating. So the closer you can get, the more energy you can extract out of it, right? You know the expansion for potential energy inversely upon R. So the closer you can get, and you can get closer if the black hole is actually rotating. So the efficiency is about nearly 42% for a maximally rotating black hole, whereas for nuclear fusion it's only of the order of 7%. So that remains the most promising scenario for a large amount of energy that we find from the nuclei of these, from the nuclei of these active galaxies, which are powered by accretion onto supermassive black holes.
No, I'll go after some time. They're still having.
So in that introduction of supermassive black holes, I will just give you a brief introduction to black holes on different scales. And there are still regions in the parameter space where we're missing the full story. And how we are actually constructing the story bit by bit, and getting a fuller picture of the demographics. But there are still a lot of open questions which I'll try to put right at the end to sort of interest you and show that any field of science, astronomy in particular, because in the lab you can tweak your equipment, change your equipment, but astronomy is one which is observed in the universe. And the universe is so rich that that it's always a challenge to understand every aspect of it. And the more data we get with more sophisticated telescopes, that it throws out new problems, just as the JWST has done with detecting galaxies much beyond what traditional models of galaxy formation made us expect. So we have black holes with a whole range of masses, from stellar-sized black holes to the most massive black holes. The stellar-sized black holes will reach up to about a couple of tens of mass of our sun. Mass of our sun is about 2 times 10 to the power 23 grams, but you can see that when you go to the most highest objects, most massive objects, we go to values of about 10 million solar masses or so. So from a few solar masses, it extends up to about 10 million solar masses. But not everything is possible, because we're still trying to find it. And that story is what I'm going to tell you for a short while before we address a couple of other questions as well. So I'm keeping an eye on the time so that I don't overshoot too much. Okay? But if you have any questions in between, feel free to ask. It doesn't matter if I don't cover everything, but whatever I cover, if you get something out of it, it will be nice. Okay? So don't hesitate to ask. And you can hear me in the back, right? No problem. One. So come back. Fine. So let's just first look at stellar mass black holes. And we knew a little bit about stellar mass black holes, and we knew a little bit about intermediate mass black holes. But it is supermassive black holes. But it is finding these intermediate mass black holes which was a challenge. And there still continues to be a challenge, a little bit of a challenge. And we will see why that is the case and how we are slowly trying to fill up that gap. You can't see from there. You can sit here actually. You can come here. I do for us.
चेयर लेके आएगी कि खड़ी रहेगी?
I don't think you can see the slides from there. You feel free very well to sit there. Now, maybe, okay, I was trying to get out of time. So maybe I will share the slides with you and brief historical outlines, although while teaching is always nice to appreciate a bit of history, that I will skip a little bit of that and I will go to actually the scientific results. But some of these, the speculation of the existence of black holes was right from Newton's time. And in fact, that light may not be able to escape, if gravity is very strong, and its origins, except that it will come back. Okay? Okay, I will not talk too much about Einstein's theory. Let me just go on to, if you have questions of black holes, you ask me, but we will just look at stellar-sized black holes, intermediate-sized black holes, massive black holes, and how they are discovered and what are the unsolved questions. Okay? Now, to measure the mass of an object, you need one thing, which is that if it is a part of a binary system, then you can go and estimate the mass of an object. Okay? There are other ways we do it as well, but that's what we do. Now, how do stellar mass black holes form? Just a few sentences to speak about stellar evolution is that stars take slightly different evolutionary paths depending upon how massive they are. The evolutionary path of a star is determined essentially by the mass of the star. A low mass star like our sun will actually evolve to form a compact object which is called the white dwarf, which is supported by what is called electron degeneracy pressure. If you're not familiar with degeneracy pressure, don't worry about it. Alright? And massive stars, which is enough to know today, that to form black holes, you really need are the end products of massive stars. Alright? So if a star is less than about 9 times or 8 or 9 times, it's slightly model dependent.
So he go back.
So,
We'll go back.
yeah, sure. So if a star, okay. So if a star is about 8 or 9 times the mass of the sun, then it will form what is called a white dwarf. And if from about 9 till about 25 or 30 solar masses, it will form what is called a neutron star, which is much denser than that of a white dwarf, but not quite a black hole. It's still an object, right? But greater than that, it will form a black hole. Don't worry about the details of the model over here, whether it's a black hole that fall back or black hole that collapse. But basically, stars whose masses are greater than roughly the ballpark of about 30 solar masses or so will end their lives as black holes. Okay? And a black hole is basically a singularity, and it is characterized by the charge, mass, and angular. Okay? And on the black hole, this is what Carl Schwarzschild worked out. The historical outline is quite interesting because in 1915, while Schwarzschild was he was director of Potsdam Observatory, but he volunteered for the war effort and was in the trenches when he received this massive packet, which contained his field equations of general relativity. And fighting the war in the trenches, he took out a little torchlight and read these notes. And within a few days, he arrived at the first solution of those equations, which is known as the Schwarzschild solution, which had a singularity but also had an event horizon within which light will also not escape. Beyond that, there is a photon sphere where the gravity would be so strong that the light would go around in circles. Then there is a light, sorry, go.
What exactly?
Singularity is basically a point source, a point. It doesn't occupy space, but it can have a massive mass. Right? In fact, the equations will actually blow up. Okay. Right? Okay. Observationally, the thing is you can't measure something which has no space, right? But you see the effects of a massive body which is very compact. Right? And which is not consistent with any other massive object. For example, a whole cluster of stars would be much more spread out than a very compact star. We know these objects are extremely compact and we can estimate their mass.
So black hole end at the center.
Sorry.
Black hole end at the center.
And effectively, the black hole is a singularity. Sorry.
That's what it says.
That's what it says.
So this means that there is no other effect.
There is no. And it said that because of the gravity of that system, it will affect the space-time curvature number. And within the event horizon, our Schwarzschild radius, you will find that material will get nice information. Beyond that, there is a photon sphere where light, the gravity will be so strong, the space-time curvature will be so large, that the photons will just go around in circles. And then there will be a last circular object, where material particles will be able to actually circulate the vacuum. It removes certain states of the object. So the maximum gravitational energy which will exist is from particles coming from infinity to the last phase of the sorry? Within from the black hole. So the radiation which you receive from it is from the material which is proceeding around it. That is where the radiation comes. Jets coming out, we are still trying to probe where exactly the jet is. So it is probably a certain distance away from, quite away from the spot jet. But how far away we are trying to probe with the high resolution observations today? We are making some progress, but I think a lot more needs to be done. Now, how did we come about the discovery of these stellar-mass black holes? These are what are known as the X-ray particles. Okay, actually, it was predicted quite early on that there could be diffuse X-rays in our galaxy, which could get reflected from the moon, and they set up a spacecraft to actually try and detect X-rays reflected off the moon. What we found was that there was a very powerful source of X-rays, which nobody has suspected. It is in the constellation Scorpius, and that is how it got its name Scope X1, which was discovered in 1962, but initially the nature of it was not clear at all. Then there was another object, or the third object which was discovered in the constellation Centaurus, third X-ray source in the constellation Centaurus, and from that we found out that this particular object, the signal actually had a periodicity. So you begin to realize that it was in a binary system. It was in a binary system, and from the and the X-ray source would get completely eclipsed for some time. So he knew that the X-ray source was actually going around the star, and when it was behind the star, you would not see any X-ray emission at all. So from looking at the dynamics of this galaxy, you could go and estimate what the mass of this object was, from which you could detect X-rays, but you couldn't actually see the star itself. All right. Now today we know that, and by using that, we actually went backwards and realized this CoX1, more detailed observations came up, were part of binary systems. So how does it after how do the X-ray emission arise? X-ray emission basically arises again by the process of accretion onto a very compact object. Okay? The gravitational potential energy, you get maximum out of it, energy extracted out of it if the object is very compact. So it has to be one of the end products of stellar evolution. Okay? And this is the neutron star of a black hole, and these binary systems are called low mass X-ray binaries or high mass X-ray binaries. And when you looked at the properties of some of these objects, you began to realize that they had to have, the only way you could understand them was by trying to invoke the presence of black holes. Now, the question you can ask yourself is, sorry.
You just said that if you're observing a galaxy, like for one example, you saw some clear in the table that you observed. I have also seen that the black hole is rotating and the
It's not a black hole which is rotating. For example, if you think of a massive star, and a black hole in a binary system. So the thing is, there would be periodicities in its yes, you can do that. Also, what happens is that, for example, if there is matter which has been excreted onto the back, it will form a efficient disk where the material which is overflowing the potential increase the output, and the rotation of the disk can also be right to the other side. So it still says plus intrinsic periodicity, which you can try and notice and get mass. So accretion is the source of energy for these for the X-ray emission which you see. Now you can ask yourself one simple question, which we will come to later, is that is there a limit to the X-ray emission is there a limit to the X-ray luminosity extract out of the object? How much can you? If I keep increasing the mass inflow, can I get very large extreme luminosities? And the answer is no. The answer is no, because what you're doing is that you're converting gravitational potential energy into other forms of energy, which is coming out as radiation, right? So the more the inflow, there will be more radiation coming out. So the radiation itself will exert a pressure as well. So there is a limiting luminosity which you can get, which was worked out by Arthur Eddington, which is known as the Eddington luminosity. And the Eddington luminosity is of the order of 10 to the power of 38 Earths per second for one solar mass object. Okay? The more massive the object is, the more luminosity you can get out of it. But for one solar mass, that is the limit. And most of the X-ray binaries are in that particular range of 10 to the power of 36 to 38 Earths per second, just in the X-ray region of the spectrum, formed due to accretion of matter from a companion star. Accretion happens by two processes. One is that if there is a low mass star, then as the star expands in its evolutionary phase, it can fill up this potential and flow out and form this accretion disk around it. But more massive stars have very strong winds as well. A sun too has a solar wind. But the more massive the star is, the more luminous it is, there is a much stronger wind which is coming out as well. So the companion compact object can also acquire matter just from the stellar wind as well. So both the processes can operate when it comes to more massive stars. We end by about 4:35, that's okay? Another 35 minutes ago. Yeah? But if you have questions in between, please ask, right? Because we do not have too much of time to answer. This is the luminosity which I was talking about, that if you look at it, maximum luminosity that we worked out is about 10 to the power of 38 Earths per second. Everyone in sun, at least for a one solar mass object, it will be 10 to the power of 38 Earths per second. But if the star is more massive, you will get more luminosity. Okay. So these are generally the area of low mass black holes. These can extend up to about few tens of solar masses. And there are many such X-ray binaries which are known in our galaxy as well as our nearby galaxy, which have been well studied and whose masses have been reasonably well studied. Okay? The thing is that if this is what's called an eclipsing binary, where orientation effects will play a role and you're seeing it completely eclipsed out, you can get a much more accurate determination of the mass. Otherwise, you'll have to take care of inclination effects as well, which can be done, but these ones give you the most accurate estimation of the mass of the galaxy. Intermediate mass black holes is actually been a bit more of a challenge, and it's only in recent years that we've been able to explore this region a bit more thoroughly than what we've been able to do before. So this I will not describe in detail over here, but basically what happens is that if you have very massive stars which are in very close interactions with one another, which you may not be even able to resolve, but you may be able to see periodicities if you make a very detailed analysis of the light curve of the signal that you see. Okay? So these are called quasi-periodic oscillations, but I'll not spend too much of time, but just remember that from the periods of oscillation, you can go and infer the mass of the object, and then you can see that once that is done, you're beginning to explore a regime. You can see these are two of the earlier papers, which are 2014-15, less than 10 years ago, where from the study of the quasi-periodic oscillations in the X-ray light curve, one has been able to get black hole masses in the range of hundreds to a few thousand solar masses. The other aspect is actually, I mentioned to you about accretion having a maximum luminosity of 10 to the power of 38 Earths per second. Now, if I have highly luminous objects, can I sort of hold my heart in my hand and say that this is likely to be a massive accreting object? So this is also being done. So the evidence is slightly less direct, but as you can see, this is a relatively nearby galaxy, which has a hyperluminous X-ray source. So the luminosity goes much beyond 10 to the power of 38 Earths per second. So if you scale up the mass, then you can understand its luminosity. And so people have looked at the variability of this object and I will try to argue that this is actually at least a 500 solar mass, 500 solar mass, so a mass intermediate mass black hole in this particular galaxy. And by looking at the light curve or distribution from very high resolution of observations, we've also been arguing that this is actually the nucleus of a relatively small dwarf galaxy where the outer stars have been stripped off by gravitational influence on a massive star, and what you're seeing is the core of a relatively small dwarf galaxy. Actually, the number of dwarf galaxies far outnumber the massive galaxies. In our local group of galaxies, we have less than half a dozen big galaxies, but there are about 50 or so plus small dwarf galaxies in our local group. And it's interesting to understand in the perspective of structure formation in our universe. Then this is a particular region in our galaxy where you can not only look at X-ray emission, but you can infer masses of objects by looking at the dynamics of gas around it. Suppose I had a compact object and I see gas moving around it, or I can see stars moving around it. If I can actually measure the velocity, I won't see the internal object, but I can estimate a mass of the object by just applying Kepler's laws of motion and inferring what that mass should be. So I can do that by gas as well. In this particular experiment which is reported, they looked at the molecular line of hydrogen cyanide. J, which is the rotational energy levels. When you learn molecular sort of spectra, you learn much more about these at quantized levels and occur in the millimeter region of the electromagnetic spectrum. And by looking at the dynamics of these galaxies, they don't see any object in the center, but from the kinematics of this object, which they can map out the velocity in different channels, they estimate a mass of about 3 into 10 to the power 4 or 10,000 solar masses. So we are slowly beginning to get more and more such examples of objects which are in an intermediate mass black hole compared to the very massive billion or million times supermassive black holes which we talked about earlier. This is another example where it's actually an object or a cluster in the Andromeda galaxy, Nebula, where from very high resolution observations we are able to look at the dynamics of gas around it and again estimated velocities, and from that they estimated a mass of the black hole component of about 10 to the power of 5 solar masses or so. This particular object is a globular cluster, but the resolution they've been able to achieve is high enough to actually look at what is in the central region over here estimated. Okay? So the other thing which I will touch upon very briefly, where we are trying to populate or understand this population of intermediate mass black holes, is from what? Something which you would have heard about, read about.
Very good.
Sorry?
It's very less.
Sorry?
It's very less. Intermediate black hole.
Let's say, no. Gravitational waves, right?
Oh.
Because the first detection of gravitational waves itself was they gave you the masses of these objects, and these were in the hundreds of solar masses black holes. So they're much more massive than the stellar mass black holes that we see. So I will not spend too much time on that because we are running out of time. I will, anyway, gravitational waves, if there is time in the end, we can answer some questions, but I will skip explaining gravitational waves right now. I'll just give you an example of the challenges of measuring that. Okay? So as you know, gravitational waves are just ripples in space-time. Just as accelerated charges radiate, accelerated bodies would actually give rise to gravitational waves, which are ripples in space-time, which will travel outwards at a velocity of light. This was worked out by Einstein way back in 1950, right? And the difference of Newtonian gravity is that, for example, if the sun jiggled around, you will actually know about it instantaneously. And if you look at the history of it, Newton himself, although he formulated the laws of gravity, he in his letters to Bentley, he said that, I just don't know the cause of gravity. And today, because everything has to travel with a finite speed, or a maximum finite speed, the velocity of light, the fact that something could be instantaneous is not consistent with the rest of physics. So the fact that, but in Einstein's theory, if the sun jiggled around a bit, it will disturb space-time, which will travel outwards at the velocity of light. So today there is a whole range of gravity wave experiments which are coming up. But just to appreciate the difficulties, what I put down over here is to look at the look at the wavelength of this radiation. For example, if there are two objects which are spiraling about each other with a period of 1 hour, which is 1 hour, this 1 hour. Okay, that's 3600 seconds. There's a factor of 2 which comes because of gravitational radiation being contributed. Even without that factor, you can get the frequency of gravitational waves from the period. You can calculate, because it travels at the velocity of light, you can get the wavelength. And you can see this is, 3.5 times roughly the distance between the sun and the moon. So it is, I mean, in this huge way, you're trying to detect a slight displacement in your equipment. So technologically itself, it's a huge challenge. And the energy which it sort of gives off is much higher when it gets closer. You can see there's a very strong dependence on the signal axis. So most of the energy is actually emitted when it is at the endpoint and coefficient. So from the theory of gravitational waves, you can go and estimate the masses, and this is the emergence. This is the first important detection where the final mass is about 62 solar masses. So this was, we are pushing the boundaries of what would have been stellar and going into the intermediate mass black hole. The gravitational waves has been, so this is another object which was detected, which was reported 2 years later. The end product is moving 42 solar masses. This is not the most recent, but not too old either. Where the blue ones are the ones which are gravitational wave detections of black holes, and the purple ones are the electromagnetic inferences. Similarly, these are neutron stars, gravitational wave detections, and electromagnetic detections. You can see a gravitational wave. It's another way that you're pushing the boundaries of the detection of intermediate-sized black holes from modeling the signal which you get. So I don't get into details of modeling right now. It's sort of range of sizes. Okay. But thinking about gravitational waves, you can see that there is a whole range on which frequencies which you can get right from the age of the universe, 10 to the power minus 16 hertz. You can imagine that what the wavelengths of this would be, and then from spiraling of supermassive black holes, which was reported recently from the timing of millisecond pulsars. Right? Pulsars are very accurate clocks, but these large gravity waves give a signal in the residuals of the timing, and then of course the gravity of the black holes, which we intermediate-sized black holes, which we talked about earlier. So this is a boundary which will keep getting pushed. People are talking about putting from the space to detect this shorter period gravitational waves, and that would be the new era as well. So briefly, go ahead.
So if you consider the sun, there are certain oscillations on its surface.
Sorry.
There are certain oscillations on the surface of sun. So can that be a source of gravitational waves as well?
Yes, okay.
Oscillations.
Oscillations, okay.
Yeah.
The thing is that what happens is that it will be extremely. Okay. The thing is that if you have a body which is just symmetrically going up and down, then you will not get gravitational waves. So any asymmetry, for example, in a rotating body, you put a clump in between and then you rotate, you get gravitational waves. So any asymmetry will give rise to gravitational waves. But if it's a perfectly symmetric oscillation, you will not see it. But you'll also, for example, the fact that the Earth, Sun is moving about the right center of mass of the system, there will be complete gravitational waves. And you can also calculate how long it will take for this to occur. It is much orders of larger than the universe. You don't have to worry about the signal is extremely compared to what you get from these inspiring devices.
Are the oscillations symmetric?
Sorry?
Are the oscillations symmetric for sun?
Actually, the thing is that the sun itself, there are all kinds of oscillations which are space and material which are not perfectly symmetric. But the amount of energy which you get out of it is minuscule. Even these ones are very small, but that can be. I'm not sure if it is actually done the calculation, but I think it will be extremely small.
Is it necessary that the speed of the gravitational wave is necessary that it is able to see?
Yeah.
With like more.
No, it is exactly the velocity of the
Like the space could contract more than speed of light, so why is it like able to see?
No, actually what happens is that what you're having is that there is a change in the structure of space-time, okay, which one can call it a ripple in the space-time. But that ripple in the space-time is actually traversing onwards. It's traversing onwards. And the velocity at which it is traveling onwards is the velocity. that comes out from the general theory of relativity. Okay? In fact, if you read the history of it, it's quite interesting because Einstein himself initially, for a brief period of time, he actually did not believe that this was the correct result. Okay? He in fact submitted a paper at the physical review, and normally Einstein's paper they just publish it. But this one he sent it to the reviewer, and the reviewer expressed doubt whether Einstein was correct. When the report came back to Einstein was so upset he actually reviewed the paper. This was in collaboration with somebody else, and the squad also said, well, that's a and they published it for 50 years. So basically, it's something which comes out of Einstein's combination with general relativity, and gravitation waves travel with the velocity of light. Okay? And these are ripples in the structure of space-time, which are traveling ripples. Okay?
So, as you're saying, like we are detecting the mass of a black hole by the objects, by calculating the speed of the object around, rotating around it.
Yeah.
So, like if a black hole is rotating on its axis, how would it affect the motion of the object revolving around it?
Okay. Okay. The thing is that when you look at from the rotation of the black hole itself, okay. Now there are two aspects of it. The two aspects of it. One is that I don't know if you'll have time to. What's the time? Okay. Another
4:30
minutes maximum. Okay. So for example, let me talk about one and two instances. From the accretion disk of a black hole, okay, I can get in the inner regions what is called the iodine fluorescence line, called the K alpha line for the inner shell of the ion, which is at 6.4 electron volts. All right. Now, if the black hole is spinning, then the position from which this you can see the line can go closer to the black hole. Innermost stable circular orbit will change and it can get closer to the black hole. Now, once it gets closer to the black hole, then the profile of the line is going to change because it will feel the photons coming out will also feel the effect of gravity more than if the black hole is stationary. All right. So in that sense, the black hole spin is going to affect the profile of the black hole. And if you solve it simultaneously, you can not only measure the mass of the black hole, but if your data is of good enough quality, you can also estimate the spin of the black hole. Okay. But on the other hand, the kind of examples which I talked about, it is too far away. Okay. There the spin of the black hole is just a mass that is going to play a role. Okay. But when you get closer, these effects become important. Yeah.
Sorry. So earlier you said the space is also expanding, like the space time is also expanding. So does like the expansion of space time have any effect on the ripple?
Not really. The thing is that what is happening is that the universe itself is expanding, right? The matrix of space time is expanding. And within that matrix, okay, for example, within that matrix, for example, you have signals which are traveling. I mean, for example, if you take the velocity of light, I mean, if you're receiving light from a distant galaxy, that is coming towards you with the velocity of light. And yet the universe is expanding. Right? So similarly, in an expanding universe, the matrix of space-time is expanding, the gravitational ripples are also coming towards you at a velocity. Yeah? So maybe 5 minutes on supermassive black holes, and then we'll take a few questions and maybe just look at the. So the techniques are actually very similar. All right? I will not get into classical here. Okay, I will not get into classical here. But basically, I'll just talk to you a little bit about the ways people have gone about. Right? Let me just talk about one or two examples. Right? So supermassive black holes, what happens is a lot of the measurements have been done for nearby galaxies, and more indirect estimates for more distant galaxies. For the nearby galaxies, you can do two things. That one is, of course, the gas which you see. Those who maybe you can resolve it. You can go and measure the redshifted and the blue shifted components. You know how fast it is moving. You know what the distance. You apply, Kepler's laws in its traditional form, or if it's very close, general relativistic corrections, and you get a mass for the object. Now, the other interesting thing you can do is that there are also radio emission which comes out from the nucleus of the galaxy. Okay. And there's all kinds of physics which are going on, And I mentioned about the accretion disk around the black hole, right? Material will have a certain angular momentum from this kind of structure. In the disks, there are examples where there are laser spots which are happening. For example, water vapor lasers. Okay. Now, laser spots occur at a particular frequency, right? So you can look at, and because radio waves can penetrate far more easily into the nucleus of the galaxy, just because the wavelengths are long, right? Wavelengths are long, absorption is less compared to optical light. So you can get far closer to the vicinity of the black hole. You can measure the shift in frequency of these laser spots. And they form this kind of structure. One side is blue shifted, the other side is red shifted. You apply your Kepler's laws or a slightly generalized GR version of it, and then you can go and estimate the mass of the black hole. So from dynamics of objects, you can go and estimate the mass of the black hole. Okay, this is one such example. I'll just show you a picture of, this is the iron K alpha line I talked about, so don't worry about that. I will just show you a picture of our own galaxy. This one is very these are objects which have been found in the center of our galaxy, where it has been, the motion has been monitored. There is an object called S2, the yellow one over there. Okay, so basically in our galaxy what has happened is that because there's a lot of gas and dust, you can't actually see the center of our galaxy optically. So they picked up stars which they could look at long wavelength infrared waves. And they monitored the motions of these stars for decades literally. And that's how Andrea Gates and Reinhard Genzel got the Nobel Prize in Physics a few years ago for actually looking at the motions of the stars. And one of them went very close to the center of the black hole. Okay? So you know that the object that you're talking about has to be smaller than the nearest passage which it went. It cannot be a huge collection of stars, otherwise it wouldn't really be able to do that, it would be interacting with the stars. And it is this object S2 which actually completed an orbit. The others are parabolic, hyperbolic orbits and has been able to estimate the mass of the object, mass of the supermassive black hole in the center of the galaxy, which is a few times about 4 billion solar masses or so. Right? We'll round up in a couple of minutes. Okay, we'll add more slides. This is my okay, I'll share this with you so you can look at it more later. Right? And some of these are very nice. Now, I'll just spend 2 minutes talking about this and then we will start. Right? Now, one of the very interesting relationships is that we've talked about determinations of masses of these black holes, right? But the mass of the black hole seems to be very intimately related to the mass of the bulge of a galaxy. An elliptical galaxy, everything is a bulge. But in a spiral galaxy, you have a bulge and then you have the spiral arms. So somehow the galaxy, the bulge of the galaxy and the supermassive black hole seems to be growing along with one another. How that relationship is established, whether it is the coalescence of smaller galaxies, is something which is still in the realm of actual research and we don't have definitive answers. But if you look at the bulge properties and the black hole properties, they are very intimately sort of related. Okay? And this particular relationship is known as the Ecology relation. So looking ahead a few questions, more complete demographics. We don't right know how the massive galaxies form 10 billion solar masses. Is it due to a coalescence? Now today when JWST is discovering massive galaxies, right when structures, we expected structures not to be there. When we find massive galaxies over there with bulges, we have to ask, how did this billion solar mass, black hole form right at the beginning? So these are new observations which are challenging our current paradigms, how it involves in relationship with galaxy evolution, and behavior of gas and utilities in regions of gravity. So obviously we need a more understanding of how jets are formed, how jets are launched. So these are all open questions which I think will require many, many more years of hard work. And this one is not really related to the last slide which I had. It's not really. How many of you have watched the pale blue dot? Okay, some of you have. Maybe I'll just play this. Those of you who haven't listened to it can listen to it. But it is when Voyager 1 spacecraft was just about to exit the solar system. Carl Sagan said, asked NASA, just point it one last time in the Earth. And this is the pale blue dot somewhere over here. These are actually artifacts over here, which is the image. And Carl Sagan's commentary, to accompany that picture is something which all of us should listen to, because today is an era when there is so much of hatred, discrimination, whether it be India or elsewhere. That it's something which I think every person should listen to. Just rethink of our value systems and the way we operate. So I'm trying to play this, but if it doesn't play, then you please listen to it on your own. Okay, let me see that. Just 2 or 3 minutes.
That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering. Thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization. Every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
That's it. So we'll stop here, right? I can take a couple of questions. PDF file with the Astro Society so that you all can
So I feel deeply honored to thank you for having, thank you for taking so much time for us and giving such a beautiful, enlightening lecture on black holes. I would like to extend my sincere gratitude to our principals, our staff advisor, our HOD, and to each one of you for your unwavering support and your active participation and making this lecture a successful one. I would like to request Dr. Sangeeta, our HOD, to present Sir with us. Thank you everyone. I would like to request each one of you to gather at the science bonds for a group photograph, and after that we'll be having refreshments.